Okay, here we go. Henry's Law, part 2. After this, I'm going to give you your assignment due tomorrow. It'll be 2 problems in the book and then a worksheet. All right. So let me finish, because I got cut off. That's what this thing does sometimes. It just stops recording. So bottom line is, the higher the pressure above the solution, the more particles stay in the solution. This has 20 dots, so that's, let's say, 20 moles of CO2, and over here, 10 moles. And the reason for that is if you cut the pressure in half, the number of dissolved particles gets cut in half. In the book, it gives you an equation. S1 over P1 equals S2 over P2. S is solubility, P is pressure. Basically, as pressure goes up, solubility goes up. And remember, solubility is how much can be dissolved at a certain temperature in a certain amount of water. You do not need to know that equation, but I am giving you a couple problems just to help you practice this concept. So that's my final thought on that. So higher pressure pushing down, more particles stay dissolved, and less pressure means less particles dissolved. That's Henry's Law, and that is only for gases, right? So Henry's Law, as pressure above solution increases, gas solubility increases. All right, so if you have a bottle of soda and you open it up and it goes psst, again, I'm using soda just because it's a good analogy, but you should not be drinking soda. I think I said that 3-4 times. Think of anything, any bottle that is capped, gases get trapped. So when you open that bottle, psst, think of anything, it makes that noise, even if it's not quite as pronounced as others. So that's the opposite of what I just wrote. When you take the cap off of a bottle, you're releasing that pressure, right? So, if you have a bottle here, look at this great bottle, okay? And you got some dissolved CO2, CO2AQ, and you have a cap on that bottle. Not a bad cap for me, right? You have a certain pressure pushing down, right? So you got CO2 gas, there's the surface, pushing down on dissolved CO2AQ. So you have CO2 gas pushing down right here on CO2 aqueous, which is dissolved. So the pressure in here, if you ever squeeze an unopened bottle of soda, it's firm. That's because there's high pressure in there. Let's say 3 atm. Well, the room is 1 atm, right? So if you open this, take the top off, what happens? Psst, what does that mean? The air pressure immediately decreases because air starts coming out of it because you have 3 atm in, 1 atm out. Gas moves from high to low pressure. You know that. So all the gas is streaming out of this thing. Well, second scenario here. So now it's open, right? Same bottle. Okay, now it's open. All that air above it and all the pressure above it was released. So air particles, CO2 particles left. Now CO2AQ, right? Take the other video I just put up. The arrows pushing down. Well, those arrows pushing down aren't there. So now these CO2 particles want to get out and there's no resistance, so they leave. They leave the solution and eventually the soda goes flat if you leave the top off. Put the top back on, it builds up pressure here, called equilibrium pressure. Eventually CO2 goes back in, as long as you keep it airtight, which is almost impossible, but it would never go flat theoretically. Now the last part here that I like to talk about solubility in gases, it's not Henry's Law, but temperature. So if you want to keep soda fresher longer, keep it cold, right? Gas solubility increases as temperature decreases. We already learned this. But it's part, I throw it in with Henry's Law. It's not part of Henry's Law, but I put it in because if you have a container and you have gases that are dissolved, CO2AQ, and you want to keep it in there, put a lot of pressure on top and then keep it cool. Put this down to like, I don't know, if we're doing Fahrenheit, just to help you understand, maybe like, 40 degrees Fahrenheit, right? In your fridge, something like that, 38, I don't know. But you don't want to freeze the water in there, but you want to keep it cold. Keep the soda out on your counter, it's gonna, go flat faster, and when you open it up, there's gonna be more gas leaving, so you want to keep it cold. So in terms of Celsius. If 0 is freezing, you know, maybe somewhere around 10 degrees Celsius, right? Or actually, no, probably more like 6, 7 degrees Celsius. But if you keep the gas cold, it huddles together, it stays down in solution, and that's how you increase solubility. The colder it is, the more you can dissolve in here. So keep the pressure high on top, that's Henry's law, and keep it cold. And if we look at this here, this is table G. I just kind of took a picture of it here. These three here, HCl, NH3, and SO2, look what happens. Start out dissolving about 82 grams of it. Follow this down. Now we're down to about, I don't know, 44 grams, right? As temperature goes up, it's like half the solubility. So more of it dissolves when it's 0 degrees. Same thing with NH3. 90 grams can dissolve in 100 milliliters of water at 0. You boil that water, hardly any of it, right? So less than 10 grams, 8 grams. SO2, you can dissolve 25. Down here at 100, increase temp, more of it's going to leave, right? If you increase temp, gas particles spread out and they leave solutions. Keep it cold, they huddle together like penguins and they dissolve better, right? So that's the opposite of all these other lines, right? Opposite of all these other lines. Okay, KCl, they all increase because they're solids. You heat them up, they dissolve better. Gases, it's the opposite, all right? So that's Henry's law and gas solubility. And that's it. I'm done with that. So you got the bookwork there. It's just 2 problems. That's going to help you practice this Henry's law concept that these 2 videos were on. I just wanted to refer you back to table G, that these lines go down. This is something you can look up. You just have to remember these are gases. So as it gets hotter, you can dissolve less of it because they leave the solution. You want to keep it cold. And then let's see. This worksheet here will be due tomorrow as well. And I'll show you before I... So right here, whoops. This word here, miscible. Stop. What am I doing? Go away. What is happening? It's because I'm... Stop. It's because of the pen. All right. So this word miscible, immiscible. Miscible means can dissolve. Immiscible means it cannot. So basically, these are making solutions and these are not. They will not dissolve, right? So this is like dissolves like. This is the opposite, okay? You're going to list who's polar, non-polar, ionic. That's some review for you there. And then you're going to say, okay, this one will dissolve in this one, but this one will not dissolve in this one. Explain why, right? Better talk about forces there. I should have wrote that in there. And then down, stop doing that. And then down here, you're going to, and I'm going to attach a Google Sheet to this because this is a picture. But I'd like you to draw if you can. You might have to send me a picture. The problem with this is drawing. You have to send a picture and email it, you know, but do the best you can with that. All right. Maybe if you want to, you know, use words to describe that, but I would love it if you could draw it and then just send me a picture. So that's going to be due tomorrow as well as the bookwork. So I'll send that right now through Google Classroom. Use these 2 videos to help with that. And I'm thinking maybe we'll do a Google Meet tomorrow or Friday. I'll text for that. Send a text to remind for that. All right. See you guys.